All right. So, in our previous lecture, we were talking about direct sum. So we were talking about the combination of subspaces and constructing new subspaces from different subspaces, right? And we said that one way to construct those subspaces was that summing up elements in the individual subspaces and ending up in another vector. And all the vectors that can be written as a summation of these vectors, which individual vectors fall into the corresponding subspace, is actually forms a new subspace, capital M, and that is shown by the sum. Where's the sign of it? The sum sign over there. And we later said that, okay, so if the sum of the subspaces can be generalized into a special condition, that if those individual subspaces are linearly independent, then we can talk about the direct sum of subspaces. And we use this notation for that. For the other one, we were using just plus sign over there. For the direct sum, we use the encircled plus sign to indicate the linear independence of these subspaces. And in the before we were talking about the linear independence of the sets or linear independence of the vectors, and now we are talking about the linear independence of subspaces. So that was requiring another definition, such that if some subspaces are linearly independent, if the sum of vectors which lies in the individual subspaces is equal to 0, that should imply that all vectors in the corresponding subspaces are also equal to 0. That is the linear independence definition of the subspaces, similar to the sets and vectors. And if that condition is satisfied, and then we can use the direct sum definition. We also saw some examples, right? So we try to define different subspaces here. The dimension of M1 is equal to 2, like in the vectors in the form of this representation. And notice that its dimension is equal to 2. We have another subspace over here, M2, and its dimension is also equal to 2. And we have another subspace over here such that x1 is equal to 0, that the first entry of the fourth dimensional vector is equal to 0, which means that the dimension of that subspace is equal to 3. And if we were trying to write some statements there, like with the sums of the subspaces, with direct sum of the subspaces. And if you have any questions here, you can ask right now so that we can clarify here. By the way, for example, for the M1 subspace, can you tell me a basis set that spans M1? So it's the M1 is composed of all the vectors such that x3 and x4 is equal to 0. First two elements are non-zero. So what might be a basis set for M1? First of all, how many elements should it have? Since its dimension equals 2, we need to have two vectors, right? With dimension 4. And for example, this might be one basis set for that subspace, right? So that any vector in that subspace can be written as a linear combination of these two vectors. Basis for M1. You can write the similar things for the M2 and M3, etc. All right. Having said that, then we talk about having defined the direct sum concept. We talk about the direct sum composition. So you can get a vector space itself, and you might have individual subspaces defined under those vector space. And if those vector the subspaces are linearly independent, And if they also if our original vector space can be written as a direct sum of these subspaces, then every vector in V can be decomposed into those subspaces, right? And so we can write every vector as x is equal to m1, m2, m3, etc., mk, such that each of these vectors fall into the corresponding subspace. And we also said that such a decomposition of x over those mi's is unique. So that's a unique composition of vectors. And there is this one remark that we wanted to fill in the next lecture, so let me write that remark as well. So let me pick another color. So if let's say vector space can be written as a direct sum of subspaces as follows. Mk linearly independent subspaces, and the dimension of M is equal to dimension of M1 plus dimension of M2 dimension of Mk. Okay. And we also saw these some examples of following the direct sum. We talk about orthogonal direct sum, right? For example, here, if R square is written as this first subspace, and one is the one-dimensional subspace here in R square, and M2 is the line which is perpendicular to it passing through the origin. And as you see over here, R square can be written as the orthogonal direct sum of M1 and M2. And notice also that the dimension of M1 subspace is equal to 1, dimension of M2 subspace is equal to 1, and the dimension of their direct sum, or orthogonal direct sum, is equal to 2, right? All right, and following that, we define the orthogonal complement of the subspace M, and we said that okay, subspace orthogonal complement is also another subspace. We showed that, and we were at the very end of the lecture. We were trying to prove one theorem, which states that if V is a vector space, and if M is a subspace within that vector space, the vector space V can be decomposed into M and M its orthogonal complement. So every vector space can be written as a direct sum of its subspace and its orthogonal complement. Okay. And notice that since these guys are also orthogonal to each other, I can also write this as well, right? So it will be also orthogonal direct sum. I can also write this as well, right? If this is true, I mean anyways, in order to say that every vector in V can be written as the two components where one of them falls into the subspace, the other one falls into its orthogonal complement, I need to show two things actually. First of all, I should be able to express the vectors as decompose every vector into those subspaces. And I should also show that M and N perpendicular are linearly independent. Okay. Do you have any questions? So what we will try to show is that if X in the vector space V is written x1 plus x2, then x1 we assume that is in M, and x2 is in M orthogonal complement. And that's what we would like to show, and we would like to start with the linear independence. Any questions? maybe I can further emphasize here. We also in the previous lecture we said that okay, here v is equal to r cube, right? And if m is given as a plane passing through the origin, okay, and m perpendicular is going to be let's say z-axis that is passing through the origin as well. And I can write, for example, r cube as the direct sum of m. Let's say this if this is x and y. Let's say it is xy plane, and the direct sum z-axis. Okay. So what I mean is that even though we are talking about abstract concepts, so they are very actual tangible, you can always find examples for such claims. And yeah. All right, so if there aren't any questions, so let's start with the linear independence condition. What do I need to show to prove that M and M perpendicular are linearly independent? So the definition of linear independence for subspace was somewhere over here, right? Where is it? For the linear independence of the subspace was saying that if m1, m2, and mk is equal to 0, then each of these vectors should be equal to 0, where all of these vectors are in the corresponding subspace. So then if we go back to our proof, so let's x1 in M and x2 in perpendicular. And it was saying that if x1 and x2 is equal to 0, the linear independence condition requires x1 is equal to 0 and x2 is equal to 0. Okay. So let's start with writing down x1 plus x2 is equal to 0. What I would like to do is that I would like to investigate the inner product of that vector with x1. Okay, so I can write that thing as x1 plus x2 and x1 is again equal to 0. Okay, and since I do have the linearity with respect to the first argument of the inner product, I can further write that thing as inner product of x1 and x1 plus inner product of x1, so x2 and x1, right? And according to our assumption over here, where x1 is in M and x2 is in M perpendicular, what is the second term over here? Inner product of x1 and x2. If x1 is in M and if x2 is in M perpendicular.
Zero.
Exactly, so this has to be equal to 0, right? Because they're orthogonal vectors. Good, and furthermore, I can write down the inner product of a vector with itself can be expressed as a norm as well, right? So I can write also about the first term, I can write norm x1 square is equal to 0. Okay. And from there, if norm of a vector is equal to 0 from the positive definiteness of the norm function, I can say x1 is equal to 0. Okay. And similarly, if you compute the inner product of, so let me write that.
Hocam o son yazdığınızı nasıl yazdınız?
Tabii şu alt satıra geçiyorum. Şöyle yazayım, şu eşittir 0. İkinci terim bu oldu. İlk terim de bu oldu. Hı?
O dot product gibi mi tanımlamış olduk?
So inner product of a vector with itself is actually defines also a norm, right? You're defining norms from the inner products, right?
Ya öyle tanımlarsak değil miydi o?
Exactly, but
Yanlış mı?
Yanlış
mı hatırlıyorum?
So from there you can use you can define a norm, and for any norm that you define there, if it is equal, it has to be a positive definite, right? So it will take the zero value only if and only if x1 is equal to 0, right?
Tamam.
Perfect. So let's save this one and continue as similarly. If we, so instead of, I just take the inner product of this zero vector with x1. Now if I compute the inner product of x1 plus x2 with x2. So since x1 plus x2 is equal to 0, that will be again equal to 0, right? And from there, you can show that x2 is also equal to 0. And so if x1 plus x2 being equal to 0 implies x2 equals 0 and x1 equals 0, then these two subspaces are linearly independent. Okay? So therefore, M and its orthogonal complement is linearly independent. Do you have any questions here? Now we will need to show the second part. Maybe I can retire the part 1. Sorry, so let's say part 1. And in the second part, we need to show that any vector x in our vector space can be expressed as two vectors, one in M and another one in M orthogonal complement. Let's say proof of 2. So let's try to do that. All right, so we'll start by trying to write down the basis functions of our subspace M. All right, so let's say suppose dimension of our subspace M is equal to K, okay, which is, let's say, less than N, which is the dimension of V, okay. And let's construct let's suppose we're given a basis for this subspace M, all right? So let M1, M2, and MK be a basis for M. So what I would like to do here is that starting from these MKs, I can use Gram-Schmidt orthogonalization technique to obtain orthogonal basis for M, right? So let's say, so let's use Gram-Schmidt orthogonalization. Sorry for my bad writing. To generate the orthogonal basis. So generate an orthogonal basis for M, such that it's composed of these vectors like M, E1, E2, and EK. Okay. So I can add further vectors into this basis set to obtain a basis for the vector space V itself. Okay, so I can complete this basis set to the basis set of the vector space V by adding n minus k basis vectors there. Okay, so let's complete this basis to a basis for V by adding other linearly independent vectors, say mk plus 1 and mn. Okay. And furthermore, I can continue Gram-Schmidt orthogonalization for this basis set and obtain orthogonal basis for the V itself. Okay, so then continue this Gram-Schmidt orthogonalization to obtain an orthogonal set for the vector space V. Okay, so let's say E1, E2, EK, and we have EK plus 1, EN. So, and note that the first K1s is actually an orthogonal basis for M, and the other ones are some other vectors that we are not showing and we are not claiming anything about, right? But since this is a basis set for V, we can write any vector x as a linear combination of these vectors, right? So let's say then any vector x in our vector space V can be expressed as x equals summation I from 1 to n, let's say alpha I ei. And furthermore, the first k element is in this falls into our subspace M. The summation I from 1 to k alpha I ei is in our subspace M. So let me save this thing and browse down a little bit. So we have this, the first part of that x that falls into M, and the remaining part, I will call that for the time being x2, and I will check if that thing is falling into the M orthogonal complement. Do you have any questions up to now here? So what I did was that I started with the basis set for our subspace, and then I just made the orthogonalization of that basis set to obtain orthogonal basis for that subspace. Then I completed that basis set by adding linearly independent vectors to a basis set for our vector space V. Okay, I add these vectors over here, and again applied Gram-Schmidt orthogonalization to this new basis set for V to obtain the orthogonal basis for the vector space V. Okay. And now I do have an orthogonal basis set for V, where the first k elements is actually a basis set for M. Right, it's over here. Maybe I can underline that. So now I have a basis set for V, which is over here, where the first k element is a basis set for M. Okay. And so if I write any x vector as a linear combination of those orthogonal basis vectors, the first k elements is going to fall into M. And there will be remaining terms. The question is, are the remaining terms in the M orthogonal complement? Okay, so let's say let x1 be these first k terms, I from 1 to k alpha I ei, and let's let x2 be the remaining terms, I from k plus 1 to n alpha I ei, such that x is equal to x1 plus x2, right? And we know that x1 is in M, but the question is x2 in M perpendicular or not? Somebody was going to ask a question.
Hocam benim bir yerde kafam karıştı ama şimdi şöyle
Hı hı,
elimizde M için bir basis var. Gram-Schmidt'te bunun ortogonallerini bulduk.
hı hı, hı.
Sonra devamında neden yani şu less complete this basis to kısmını neden eklediğimizi anlayamadım.
Tabii, çünkü the reason is that we would like to obtain orthogonal basis for the vector space V, because what we would like to do is that what was the main goal of the theorem is that we would like to show V can be written as a direct sum of M and M its orthogonal complement, right? So what we did was that we first obtained an orthogonal basis set for this subspace, all right? And then we completed and make another orthogonalization and obtain a full orthogonal basis for the vector space V. And what we would like to show is that let's have a look at the remaining vectors if they will fall into the M orthogonal complement. Okay.
Okay.
So by using that, by adding those vectors and applying once again the Gram-Schmidt orthogonalization, we were able to write this. So the answer to your question was this. So we were able to write this, right, by adding those vectors. And we also have the first k elements in our subspace. So to obtain such a decomposition, we completed and applied the Gram-Schmidt technique. Does that answer your question?
Yes.
Perfect then. So we are almost done with the proof. So I just wrote the first k elements as x1 and the remaining terms as x2. So I know that x1 is in M, but we don't know if x2 is in M perpendicular. And so if x2 is in M perpendicular, then I should have inner product of x2. So that's, sorry. Let me use the inner product sign. So the inner product of x2 and the n vector in our subspace M should be equal to 0, right? For all M vectors in M. So that was the definition of the orthogonal complement of a subspace, right? You compute the inner product of the original vectors and that should be equal to 0. And notice that if M is in the subspace M, then M can be written as a linear combination of these vectors, right? So let me write it over here. Notice that M is in that capital M, and this was these are the basis for our subspace M. Then I can write M as a, let's say, summation j from 1 to k, let's say beta j ej, right? And x2 was simply given as I from k plus 1 to n alpha I ei, all right? So I can write the inner product of x2 and m as, so I will use that expression for x2. So it is equal to summation I from k plus 1 to n alpha I ei, and m can be written as summation j from 1 to k beta j j. Okay. And notice that since we constructed the orthogonal basis for V, I can simply claim that EI, inner product of EI and EJ is equal to 0 for when I is equal to 1 to k and j is equal to k plus 1 to n. So it's the vice versa j, it should be I. Because they were orthogonal, right?
Mm-hmm.
So then that pretty much like completes the proof. So because then I will show that I was able to show that inner product of x2 and m is equal to 0 for all m in M, right? Which puts x2 in M orthogonal complement. And we show that any vector in X can be written as x1 plus x2, where x1 is in M and x2 is in M orthogonal complement. Furthermore, in part 1, we showed that M and M orthogonal complement are linearly independent. Then I can write down as a consequence of that, V is equal to M orthogonal and M orthogonal complement. Okay. So any vector space V can be written as a direct sum of a subspace M and its orthogonal complement M perpendicular over here. And here was one example, so where M was this plane passing through the origin, and M perpendicular was the line, Z line actually, right? And once again, here we have again another example. If M1 and M2 are perpendicular to each other, here M2 is equal to the M1 perpendicular actually. So this is actually N1 orthogonal complement, and R square can be written as M1 plus M2, M1 direct sum, M1 perpendicular. Let me remove those comments that I add on while commenting, not to confuse you later. So basically the Gram-Schmidt technique was useful for us. We will use that later on as well in different applications, such that we can prove our claims, such theorems. That's the reason why we learned this Gram-Schmidt orthogonalization technique. Just like that, so just like we learned Gram-Schmidt orthogonalization technique to prove this theorem, we will use this theorem to prove the next theorem, and that's the projection theorem. Do you have any questions?
Hocam birkaç saniyeliğine yazdığınız şeyi yazsınız.
Tabii, buyurun. And in the meantime, if you have questions, I can try to answer or explain better.
Teşekkür ederim.
All right, so our next theorem is the infamous projection theorem, and we will also make use of this orthogonality concept there. But let's see what this theorem is about, and we will also try to prove that, and then we can also try to understand its interpretation. So let's start by reading it, okay? So the projection theorem states that let H be a Hilbert space, and we know by this time that a Hilbert space is the inner product space complete with respect to the norm induced by the inner product. And so let H be a Hilbert space and let M be a finite dimensional subspace of H. Okay, so we are given an H and its subspace M. So for any vector X in the Hilbert space, our vector space, the following minimization problem has a solution. So among all possible vectors in our subspace M, I can find one vector which minimizes the distance between X and M. Okay, so among all possible vectors in my subspace M, I can find a vector such that minimizes the distance between the given vector x and the m's over here. And its interpretation is that we can find the closest vector to x lying in the subspace M. So that's what we like to do. And to prove that, we will start with using our previous theorem. So we will first write down H as a direct sum of M and its orthogonal complement. And so by this will be a decomposition of any vector into M and M orthogonal complement, so that any vector let's say for any vector given in the vector space H, so X in H, okay. So there exists x1 in M and x2 in M perpendicular, such that x is equal to x1 plus x2. All right, so that comes from that comes from being able to express the vector space H as a direct sum of M and its orthogonal complement. And furthermore, this decomposition is unique, right? So because we showed that if we are given a decomposition where we have these subspaces that are linearly independent, then this decomposition x1s and x2s are unique, right? Maybe I can write that thing as well. Note that this decomposition is unique. Okay. So what I will do next is that then I will have a look at the norm of the vectors, the difference of the vectors in M subspace and the X itself. So we are given an X vector, and I would like to look at the norm of the difference of that X vector and the vectors in my subspace M. Okay, so let's say let Fm be the norm of the X vector and the M vector difference over here for these M vectors in our subspace. So Fm is defined as follows: norm of X minus M. And notice that I can write that thing as instead of X, I can write X1 plus X2 minus M here. And furthermore, I will assume that since M is in our subspace and X1 is in our subspace as well, I can write their difference to lie in the subspace M as well. So if I rearrange the terms and write down x1 minus M plus x2, then I can claim that, where's the pen over here, the first term is a linear combination of two vectors in our subspace M, therefore it's another vector in our subspace M. And the second term is still in M orthogonal complement. Okay. So the next thing I will do is that I will inspect the norm square of this expression over here. So let me write it down to pass to the inner product. So let's try to inspect x1 minus m plus x2 norm square, which can be written as the inner product of x1 minus m plus x2 and x1 minus m plus x2 itself. All right, and now I can use the linearity of the with respect to first argument and also the second argument. I can use to write these thing as the x1 minus m and x1 minus m. And I will have the product of x1 minus m and x2. And I will have the product of x2 and x1 minus m. And I will have inner product of x2 and x2. All right, so what can you tell about these terms in that appeared in the middle, these cross terms? So we are computing inner product of vectors. One is in our subspace M, the other one is in M complement. So that thing is equal to 0. So I said, or I should say orthogonal complement. So this is 0, and that is 0 as well, right? Okay. Then this norm square, which I was given as fm, so it is the fm square, can be written as, I can write these inner products as the norm squares as well. So norm of x1 minus m square plus norm of x2 square. Okay. So we are looking for the m vector which minimizes this fm function over here. And so when I'm changing the m vector, I am changing the value of fm, and I'm obtaining this expression over there. And I would like to ask at this stage, what is the minimum value that I can achieve for fm square by changing m? By indicating that the norm functions are getting always positive values, non-negative values.
0.
As a matter of fact,
MBQ's x1.
exactly. So the thing is that this x2 square is always remaining there, right? So I should first write there this, the left-hand side is always greater than or equal to norm of x2 square, right? So the minimum of fm squared has to be greater than the norm of x2 square over here. And that minimum can be achieved if m is chosen to be x1, right? So let's write minimum of fm is achieved. So this is the sum of two non-negative numbers, and the second one we don't have any control of it. It's given when x is given and m is given. But the first one we are changing by changing m over there, and the minimum value of the norm is 0, and that gets the value 0. The norm function gets the value 0 if the inside the norm is equal, the vector itself is equal to 0. Okay, so minimum of fm is achieved by selecting m to be x1. Okay. So therefore, this in the theorem we were saying that this minimization problem has a solution, and actually this value m being equal to x1 is actually the solution to this problem. Okay, so this, let's say I will say m star among all possible m. One of them is minimizing this cost function over here, norm of x minus m, minimize fm as well. So the minimum is achieved by choosing m as x1, and furthermore m star is unique. And the reason why M star is unique is that the M star is equal to x1 and x1 is unique, right? So let's write because you write as because x1 is unique. And why x1 is unique? Because the composition of the x vector on M and M orthogonal complement is unique. And one last remark I will say, and furthermore, if I look at the difference of x and m star, which will be the error actually among all possible m's, that will be simply equal to x minus x1, and that is equal to x2, right? And notice that x2 is orthogonal to m because x2 lies in the orthogonal complement. So x2 is orthogonal to our subspace M. So if we would like to then express a pictorial representation of the theorem, it will be something like that. If I can draw, let's see. So let's pick a color like this. And suppose we are given a subspace M. Okay, let's say something like this. All right, so suppose this is our subspace M. Wait, sorry, let me grab my pen. So suppose this is M, all right. And suppose we are given a vector which doesn't lie in M, so it is, let's say, like something like this, okay? So let's say it's something like this. This is the X vector. Then what I'm looking for is among all possible vectors that lies on M, I'm looking for the one that is closest to this X vector, all right? And the theorem states that you can get the decomposition of X and its orthogonal component, so complement. So let me pick another color over here. So you can get this X vector, all right? And let's say this is the composition of X on this M subspace. And let's pick another color. And plus, this is the orthogonal vector x2, okay, which is in M orthogonal complement. And the theorem states that this x1 is equal to the M star, where we have the closest point in our subspace M, that minimizes the distance between the given vector x and the n vector in our subspace M over here, okay? And the error between them is x2 is orthogonal to the subspace, our solution and the subspace. So let's write x2, which is equal to x minus M star is orthogonal to M. Also, it's orthogonal to x1 because x1 is also in M. So it says that the error is orthogonal to the subspace, error is orthogonal to solution itself as well. And that's being claimed by the projection theorem. So in our next lecture, we will talk once again about the projection theorem, and we will see its applications. But before that, do you have any questions?
Hocam error'ı biraz daha açar mısınız? Ben neydeki hataya bakıyoruz onu anlayamadım.
Tabii şu fonksiyonun hani biz kendi subspace'imizle içerisinde eksi en yakın olan vektörü bulmaya çalışıyorduk ya. Bulduk, o yeşil vektörmüş, şu x1'mış. X ile x1 arasındaki fark da bizim error'ümüz olmuş oluyor işte.
Anladım hocam.
Tamam mı? Distance'ımız gibi yani. Böyle biz o error'ü minimize etmeye çalışıyoruz aslında. Hani x ile seçebileceğimiz en vektörler arasındaki distance'ı minimize etmeye çalışıyoruz. Error'ü minimize ediyoruz. Minimum distance'da bu m star'ın işte şey nedir o x1'e eşit olduğu durumda, yani işte x'in m üzerindeki ortogonal projection'ı hesapladıktan sonra bulabileceğimiz değeriymiş. Bu durumdaki error'ümüz de dik olurmuş. Yani
Hocam ama x dediğimiz şey subspace M'de bir şey değil mi? Hani açıklamada öyle demiştik.
yok, x is a vector in our vector space H.
Ha ben şurayı yanlış okumuşum. X lying in the subspace M diyor ya. O vector için onu söylemiş galiba. Closest vector.
For any x in H.
Yok altta IE var ya hocam.
Yeah, we can find the closed vector x lying in the subspace M. 2x diyor. We can find the closed vector 2x diyor. So closed vector x demiyor. M subspace'te, x Hilbert space'te, vector space'te.
Tamam.
Süper. So that M star is unique, and I don't know, so maybe I can pick another picture representation. So this is the optimal solution where you get the minimum distance, and for example, this cannot be an optimal solution, right? This cannot be M star, and that error is not going to be perpendicular as well to the subspace. Anyways, we can maybe talk more in our next lecture on Wednesday. So we will continue with the projection theorem and its applications.